Hello guys, welcome to the video. So right now it's late night and I'm in the roof, but I thought of recording this video because I read about something interesting, just an interesting idea regarding entropy. Why entropy increases in our universe, and what has quantum mechanics got to do with it. So I recently published an article on the quantum mechanical origins of entropy, in which I shared some of my ideas. I should say hypothesis. It's not really a research article. It's more of a hypothesis, but there I shared about my views on this topic and why the uncertainty principle in quantum mechanics might provide some room for entropy to increase. I used some arguments from very basic statistical physics like phase space and everything. The phase cells, why we divide the phase space, the x versus p space into finite volumes and all this stuff. So yeah, again that's an hypothesis, and my claim was that because there is some uncertainty at the quantum level because of the quantum uncertainty principle, there is some room for entropy to increase in the universe. However, I did not claim that entropy increases in the universe because of quantum uncertainty. That would be too far-fetched, and if I made that claim, there is I have no justification for that. Why does entropy increase? Well, see, it depends on how we define entropy and everything, and I think that has got to do with the arrow of time. Then even in arrow of time has also been discussed in detail in that article. I'll give the link in the description if you want to read it. I have discussed all the three arrows of time, mainly the cosmological and thermodynamic arrow of time. The psychological arrow of time is not very relevant for this article, but yeah, I recently read about this idea that entropy increases in our universe. First of all, they say that entropy is equal to information. Now, I have discussed this in many of my videos, definitely one or two of my videos, that entropy is definitely related to information, very closely related to information, but entropy is not necessarily equal to information. There is not a positive correlation between entropy and information. It's not like as entropy increases, information keeps on increasing. No, that is not the case. Because, for instance, before everything, before the Big Bang, when at the beginning of everything, we don't know whether the Big Bang model is the correct model, and even if it is correct, whether it was the beginning of time. But the point is, before Big Bang, the general view is that before Big Bang there was nothing. Right? It was just nothingness, empty nothingness, void, and that is definitely a very low entropy state because there is no disorder at all. Disorder is not the very accurate definition of entropy. Entropy is the number of possible configurations. But if you don't have any particle, if you don't have any matter, if you don't have any variation in the void, then how can you even define a configuration? So in that sense, it's the lowest entropy state. And information, if you talk about information, okay, information is zero because there is no information at all. You don't even need any notion of information, any concept of information, because you don't have anything yet. Then the Big Bang formed. It's just a tiny dot, single point in space-time, but it's very, I shouldn't say it's a point in space-time because space-time is created as the universe expands, but it's a very tiny dot and very contains a huge density of energy, but it's a very tiny dot, right? That's the Big Bang. So then as the universe started, I think you can hear the train horns because this place is very close to the railway station, and in the night it's quiet. Everything else is quiet, so you can. And I'm on the roof in open air, so this sound is pretty loud. The train horn, the train honk, and everything, locomotives and all. So basically, yeah. So Big Bang, as the universe started expanding in the early universe, it was still a relatively low entropy state because we know from observations that the universe is the early universe was very smooth. If there was even a small amount of inhomogeneity, then the force of gravity would have caused the universe to collapse on itself, and the universe wouldn't have survived for 13.8 billion years, and we wouldn't be here discussing all of this. So this smoothness is actually this means low entropy because it's perfectly smooth. There is no not much variation, and it was anyway a very small area, small volume. The universe has just started expanding from a dot. It has not yet become so large in the early universe, in the initial phase. So then entropy was slowly increasing because then as the universe expanded, then radiation and matter decoupled, and then the first stable atom was formed, and then stars were formed, nucleosynthesis, and then all of this, so on and so forth. Galaxies were formed, structures were formed, more and more elements were formed in the stars, and eventually in one planet Earth, and maybe in some other planets also, we don't know, life was also formed. And this is complexity. This is entropy is increasing. Of course, as the universe evolves, entropy always increases with time. We cannot question this, second law of thermodynamics. So now entropy is increasing, that's very well, and information is also increasing, because think of the very early universe. It was smooth and everything. You don't need a lot of information to describe that universe. Today the universe is huge and it's expanding. You have a lot of things to explain. In some planets you have life and all these complexities. You need a huge amount of information. So it seems like as entropy increases, information also increases. This is true only up to a point, but after a certain point, even the entropy will keep on increasing, the information will decrease. Why? Because see, as the universe is expanding, what would happen? I mean, where is the universe headed ultimately? What we call the thermodynamic, I mean the heat death. Because as the universe is expanding, it's cooling down, and as it's cooling down, on average the temperature of the universe is also decreasing, and the universe is becoming, it's reaching towards equilibrium, thermal equilibrium, thermodynamic equilibrium. Because see, right now in the early universe, it was very, energy was very high. Then the universe is cooling down, and at the end stage of the universe, when the universe will reach its highest entropy state, maximum entropy corresponds to perfect equilibrium. Then it would be, equilibrium means there would be no energy transfer between any two parts of the universe. That means no life, or not even life, I mean leave alone life, no structures would exist as such. Because for a structure to exist, for a galaxy to exist, you are able to distinguish that this is a galaxy, surrounding it is just empty space. But then there would be a large number of particles, highest entropy state, but all the particles, there would be a large number of particles, but all the particles would be uniformly distributed throughout the entire universe. So that there would be no variation, there would be no structures, there would be no, like, nothing. So in that sense, information would again be very less. Because you don't need a lot of information to describe a state. Maybe it's a huge universe, almost extending, for all practical purposes, we can say it's extending infinite in all directions. But if the number of particles, huge number of particles, but everything is arranged uniformly, there is no variation in density, no exchange of energy, it's perfect equilibrium. And the particles are, they're colliding among one another randomly, but overall the system does not change with time in its entirety. If you look at the entire system, you just see particles everywhere. It's no change. So you don't need a lot of information. It's actually equivalent to the state before the Big Bang, because you don't need to describe anything. It was nothingness then, and now also it's technically the same thing everywhere. So if you ignore the information about the constituent particles, these are all elementary particles, then informationally it's on the same footing, the beginning and the end. So the lowest entropy state, the beginning, and the maximum entropy state, the end of the universe, both of them correspond to minimum information. So information starts from zero, then it increases up to a point as the entropy is increasing. Then it starts decreasing. Entropy is still increasing, but information starts decreasing, and then at the end, at the maximum entropy state, the information again drops back to zero. You can think of it like this. That is my view, actually. Not my view. Many physicists believe this, but this is the view I agree with. You can also see a good example of this in, if you study black hole information paradox, we have this Page curve proposed by Don Page. The entanglement entropy of the black hole is plotted as a function of time. This time is the lifetime of the black hole, since the black hole is formed, and then up to when it's evaporated away completely. When it evaporates away completely via Hawking radiation. And this entanglement entropy, although we use the term entropy, this is actually a measure of information. To what degree the particle inside the black hole and its partner particle outside the black hole, they are correlated. So actually we're plotting information over time, and it increases and then decreases with time, as we would expect, even in general, even beyond the black hole. A very good analogy is like white color. Like it's just pure white color, nothing, and then you mix the 7 colors, so I can get back the same white color. So it's kind of that, just an analogy. So now this the idea that I was reading about, that I mentioned, it claims that entropy increases in our universe because information is created during every quantum measurement. Okay, so first of all, my objection to this view would be that if you say that information, if you say this, then that means you are saying information is exactly equal to entropy. That means as entropy, if information increases, entropy always increases. But as I told you for the last few minutes, that may not be the case. The relation between entropy and information is not a linear positive correlation, right? So this is one problem. Another problem is basically the idea goes like, when you make a quantum measurement, before you make a quantum measurement, according to quantum mechanics, the quantum system exists in a superposition of all possible states. It doesn't exist in a fixed state, right? So since it exists in a superposition of all possible states, what this means is that you cannot really before the measurement you don't know the exact state of the particle, so you don't have any information about the state of the particle. That is what it seems to be. Now my question would be, although this is a very, I'm not sure if this is exactly accurate and correct, but my question would be, is it correct to say that we don't have information about the system before making the measurement? We don't have information about the exact state of the system, exact state in which we will find the system after measurement. That is where the randomness is. Quantum mechanics is random, probabilistic. That is where the randomness lies. We don't know after the measurement what state we will find the system to be. But even before the measurement, we already know the state of the system, that these are the possibilities we can get. These are the possible measurement outcomes. That state is actually well defined in many cases. So I don't think it's exactly correct to say, correct me if I'm wrong, I may be wrong, but I think it's not correct to say that we have no information about the system at all before doing the measurement. Of course, we have less information about the system before as compared to after the measurement, but it's not correct to say we have no information at all. It's not totally random. Number one, because we can calculate, we can know what are the possibilities, and we can also calculate the probability corresponding to each possibility. What we cannot do before the measurement is we cannot exactly predict that what this particular measurement outcome will be, because under the same conditions, if I carry out the measurement one more time, I can get a different outcome within the possibilities, within the set of possible outcomes. The next thing is, according to this idea that quantum mechanics, once you do a quantum measurement, then you gain some information about the system. I have no objection there, that's true. Once I do a quantum measurement, I gain some information. I know that, okay, this is the particular state of the system right now. But then they say that this means information is created, and that is why entropy is increasing, because information is created, information is equal to entropy. I already told you why I have objections there, that information and entropy has a positive correlation forever. I have an objection there. Number one. Number two, okay, information in a way is created when you make a quantum measurement. I'm not sure if information is created locally for that particular quantum system. You definitely gain some information. So in that sense, maybe information is created for that particular system locally. But if I consider the entire universe as a whole, then is it really true that information is created, like new information is created every time a quantum measurement is being carried out? Then this is somewhat analogous to the many worlds interpretation, parallel worlds theory. Like it's an interpretation of quantum mechanics, that every time a quantum measurement is made, the universe branches into different possibilities, in the many different branches of the universe are formed, and all the possibilities take place in, let's say there are two possibilities, so the universe will branch into two parallel universes, and each of the possibility will take place in the two universes. Possibility 1 will take place in universe 1, possibility 2 will take place in universe 2. But according to this many worlds interpretation, the theory says that these branching universes, parallel worlds, if you want to call them parallel worlds, they cannot communicate among one another. So then this is not even a scientific theory in a way, because since these universes are non-communicating, we cannot do any experiment or we cannot even hope to get any experimental evidence that these parallel universes actually exist. So this theory is not, strictly speaking, it's not falsifiable. So we cannot know whether this theory is correct or wrong. We can neither prove it nor disprove it. There are some elegant features of the many worlds interpretation, because it's completely deterministic. The time evolution of any quantum system is actually deterministic under Schrodinger's equation. The randomness, as I told you, it lies in the measurement. But if you make the assumption that every time you make a measurement, the universe branches out and all the possibilities take place, then you get around the randomness problem. So it's a completely deterministic interpretation of quantum mechanics. But due to this lack of experimental support, and not just lack of experimental support currently, the theory is such that it's not falsifiable, probably. So that is the biggest downside. It may be true, but there's no way to verify it. So it's not even a scientific theory, because you cannot gain a lot of new prediction or anything out of it. It may be a very comfortable way of thinking about the world, or maybe not so comfortable for some of you, because again, parallel worlds, we can never communicate with this world. So what is the point of talking about them? You understand, right? There's a lot of debate going on. Some people are, I cannot deny that definitely the parallel worlds interpretation, the many worlds interpretation has its plus points. But overall, I'm not very, I'm not a huge, right now currently, maybe at one point of time I was, but right now I don't like this interpretation very much. Now, do I like the Copenhagen interpretation? Of course not. To be honest, interpretations of quantum mechanics, most interpretations, they have their ups and downs, but I cannot say, I think none of us can say confidently that this interpretation is correct and that is wrong. We don't know enough about the foundational aspects of quantum theory. I think it's too early to say that. So these are just interpretations, right? And yeah, so what I was saying was that so once you make a quantum measurement according to this whatever I was reading, I'll try to give the link, but it's actually I even forgot whether it was an article or a YouTube video, because today itself I got a notification and I watched a video on YouTube where they make this claim. But then in the video, the creator, the YouTuber, whoever was making the video, he said that he actually read about this in an article. Now, but unfortunately, in the description of the video, the article link was not given. Anyway, I think I'm just discussing the idea with you guys. So even if I cannot give the resources, it won't be a big deal, because I myself have not read. If there is an article or any paper regarding this, I have not read it in detail. I'm not even sure if this is just an idea or if this is a well-researched paper or anything. But yeah, then they're saying that every time we make a quantum measurement, a new information is being created. I disagree with that. Locally, you are gaining some information about that particular system, but I don't think that as a whole, if you look at the universe as a whole, information is being created. It could be like the total amount of information in the universe, I believe, is constant. Okay, but information might go through different forms. Okay, like, and not all of this. This is just a very hypothesis. This is just a way of. I mean, take this as a hypothesis. Don't take it as a claim or as a scientific theory or anything. Whatever I'm saying, I'm going to say right now. So I think the universe, the total amount of information in the universe is constant, of course, but information can exist in various forms, roughly speaking, and it's not possible for us or our measuring devices, or maybe even our theories, to grasp or to perceive all the different forms of information. So in our perception, the amount of information can, it may appear that information is being created, because quantum theory is not a final theory. It doesn't take into account gravity. We cannot, it's very likely that in the future we'll find some more general, more fundamental theory which will be an extension of quantum theory, because after all the experimental support, I cannot say quantum theory is wrong. That's not what I'm saying. But quantum theory, all the predictions of quantum theory need not be correct as they are in their present form. So what I'm saying is that when you make a measurement, quantum information is being created. You are making this claim. Maybe this is not the best way to put it. So what is the best way to put it? I can give you some rough hypothesis, but probably we'll get the answer in the future once we find some more general theory, more unifying theory. Because quantum theory in its present form is definitely not a complete theory, albeit a very successful theory. So my rough ideas would be, hypothesis would be that, like I said, when you make a quantum measurement, you gain some information about that particular quantum system. But I think this information was already there. I'm not talking about hidden variables. I'm not talking about any hidden variables theory. I'm aware of all of this. So please don't comment. I'm aware of hidden variables theory. I'm not talking about hidden variable theory. And again, even if you think about that, then this debate between locality and realism, Bell's inequality, and even recently there is this debate about macro realism versus non-invasiveness, Leggett-Krag inequality. This is again an open question. It's not yet a resolved question. But personally, I think we cannot say that when we make a quantum measurement, the information is being created. It's more like we gain some information about the system. This information was in some different form prior to the measurement, and in what form? Well, I think the answer is that we don't yet have a theory that can give us the answer. We need a theory, unifying theory beyond quantum mechanics for that. Now you might think that this answer is a very vague answer. I'm trying to cover up the problem by just saying that we don't yet have a theory that can, but this is what I feel, and there is some logic behind it. It's not like I'm trying to cover up the problem. If you think about it, using present knowledge, whatever whatever answers you will be getting, those answers are not complete answers. So I think it's okay. What is the problem in accepting that our present theories are not complete? And definitely we will get a better answer in the future. That's what I think you can see the moon, because it was very dark. The moon was under the clouds when I started recording the video, but now you can see the moon, right? Anyway, so yeah, so that's what I'm telling. So I'm not sure whether you agree with me or not, but I think this idea that information is being created every time we make a quantum measurement, in a way, yes, but that depends on what you mean by information. Fundamentally, I don't believe information can be created or destroyed in the way that this idea, according to this idea, whatever I understood it. Maybe I am missing something, because I have not talked with the people whose I'm not very sure about the source of this idea even. But yes, it was something like this. Anyway, yeah, I think that's all for this video. So and one more problem is that they claim that information is equal to entropy. So every time we make a quantum measurement, the information is being created, and that's why entropy is also being created. I mean, it's kind of entropy generation, and entropy is increasing. Definitely an idea to worth thinking about, because even if it's wrong, thinking about these along these lines might give us some new insights. But again, I'm not very convinced. In my opinion, okay, in my opinion, why entropy increases in the universe is might be first of all, it might be a statistical question. It might be a question which does not have any definite answer as such. It's not a question which we cannot explain. It's a fact. Then there are some more recent approaches, like there was a paper by Julian Barber, if I remember the name right, of Oxford University, if I remember it right, and they said that although I'm not saying the results of the paper are conclusive and they are evidence in support of whatever I'm saying. That's not what I'm claiming, but basically what the paper said was that they started with some particles and they did some simulations. Although these were very simple simulations, they only took into account Newtonian gravity, not the relativistic, not the Einstein gravity. So then they did this, and what they found was that there could be two arrows of time. One is pointing in the opposite direction, one is pointing toward the past, one is pointing towards the future. So basically at the Big Bang, two universes could have been created with two opposing cosmological arrows of time, and we are in one of the universe. So in the other universe, again, it's kind of like parallel universe domain. So but this is they have done this the other simulations, and they have got this result that entropy can increase even in a contracting, not contracting universe, I should say, in a universe where the cosmological arrow of time points in the opposite direction. So in some sense, it could also be the case that entropy could increase in a contracting universe, because entropy is not about the spatial configurations only. You say that the universe is expanding, so the volume available to the particles is expanding, is increasing, so the particles can be in many more different arrangements or configurations. So entropy is increasing. That's true, but if the universe was contracting, then this volume is definitely decreasing. But even then, the particles would collide with one another, and then the number of possible ways in which energies and velocities being transferred among them due to these collisions, that might increase. So yeah, you cannot say that if the universe is contracting, entropy would have to decrease. We cannot make this a general claim. Yeah, in some cases, it could decrease also. So yeah, I think that's what I wanted to discuss in this video, and I'll try to give the link in the description if I find it. Otherwise, just I mean, even if I cannot give you the exact resource or exact source of what this idea, just I still think this is an insightful discussion, the whatever I discussed in this video, because, and I would definitely like to know your comments about on this, your opinion on this in the comments. I'm sorry, I was just, this is it's right now it's 3:30 a.m. in the night, and I just finished doing some work, and I just thought of coming to the roof to get some fresh open air, and I thought of recording the video. As you can see, I'm not even wearing my spectacles, so this was not a planned, like I'll do a video. It's just a sudden idea, and I just want to go to sleep right now. So I hope you'll pardon me, but yeah, thank you for watching.